Okay, so now what we're going to talk about is a review of logarithms. So there are four main properties that we're going to talk about, but before we do that, we need to talk about what a logarithm is. And we use logarithms as the inverse of exponentials. So for example, if we have 3 to the x equals 27, you might be able to answer that equation by yourself without even really doing any solving. You might look at it and say, well, 3 to what power gives us 27? Well, 3 to the first is 3, 3 squared is 9. So 3 to the third, oh, that's 27, so x must be 3. That's great, but where logarithms comes into play is, what if that problem said 3 to the x equals 32? Well, you might look at that and you might say, well, I know it's got to be more than 3 and less than 4, so it's 3 point something, but other than that 3 point something, how are we going to get a really precise answer? And so that's where logarithms come into play. A logarithm basically asks that question in itself. So if I have the question, 3 to what power gives me 32, I can write that as a logarithm, log base 3 of 32. This logarithm and this equation are asking the same thing. 3 raised to what power gives me 32? And so that's where logarithms come into play, and they're really useful in helping us solve those kinds of exponential equations. The reason that we can use them to solve exponential equations is because exponential equations and logarithmic equations are inverses of each other. So we can use them to undo each other when solving equations. So for example, if you had 2 to the 3x plus 1 equals 51, we can use a logarithm to undo that exponential, and we can take the log base 2 of both sides. On the left side, that leaves us with 3x plus 1 equals log base 2 of 51. You can evaluate log base 2 of 51 on your calculator and then finish solving x from there by subtracting 1 and dividing by 3. So that's why logarithms are useful, but not only are they useful for solving equations, but we need to know how to use their properties to make solving equations more effective. So let's go ahead and talk about the four main properties. So the first property we're going to look at is called the product property. And for the product property, that is when we have something like log of A plus log of B equals. Now, if I don't write a base on that log, that's a common log, and we are to assume that the base is 10. So that's log base 10 of A plus log base 10 of B equals what? So this log property is called product property. Anytime you see this plus sign between two logarithms, you can combine these two logarithms, also called condensing, and make it a product of this A right here and this B right here. So log base A plus log base B gives us log of A times B. So we can multiply those two numbers and condense it into one logarithm. That's our product property. Then we have a similar property called the quotient property. And this time I'm going to use a different kind of well-known log. If I write ln of A and ln of B, if I have ln and don't write the base, it's because I'm assuming that the base is base E. That's natural logs. Always have the base E. So now when I have that subtraction symbol between two logs, that right there is what tells us that we are, instead of multiplying, we're going to divide. We can condense it into one log, and the item that's being subtracted becomes the denominator of our fraction or of our quotient. So natural log of a minus natural log of b equals natural log of a over b. Now, those two properties, those just come from exponent rules, right? If we think back to our exponent rules, if we have x squared times x cubed, the product, what we can do is condense those into x to the fifth, the sum, right? 2 plus 3. Well, it's the same thing, except logarithms are the inverse, so it's going backwards. Log of a plus log of b is now then the product, same as before. Here we have the multiplication and addition, right? And here we have addition and multiplication. Those properties go together and they come from each other. Now, a third property is called the power property. And the power property, let's say I have log, and I'll just do a common log. Let's say I have log of a to the second power. That's the same thing as pulling that down into the front and saying 2 times log of a. So that 2 can be an exponent right here on the a of our log, or it can be in the front and say 2 log of a. Again, that comes from our exponent properties. And so that's all we need for power property. That's really useful, and you'll see why in a future problem. And then the excuse me on that. The last property that I want us to talk about, and I'm running a little bit out of room here, but is called the change of base. And the change of base, let's say we have log, let's just say log base x of y. Well, sometimes it would be more helpful for us if that log had a different base. And this used to be even more relevant because, believe it or not, our calculators didn't used to allow us to calculate a log with just any base. It had to be a log base 10 or a log base e, a common log or a natural log. Now you guys do have the ability to do that with your calculators, but that doesn't change the fact that sometimes it will be more helpful if you can change that base. And the way that you change that base is to make it a quotient of two bases, of two logs. And the new base can be anything you want as long as it's the same. So I'm just going to call that log base z, okay? And it can be anything you want. It could be log base 10, it could be log base e, it could be log base 3, it could be anything you want as long as it's the same. And then it's the y is on top and the x is on bottom. So log base z of y over log base z of x. That's the same as log base x of y. So you're splitting it into two logs, the quotient of two logs, and that way they can have any base they want. So now let's go ahead and look and see how this can all be applied together. So these properties are all really important, but let's look at how we can use them. Okay, so looking at this problem, this is a really common IB style question. So when we look at this, you're going to see probably more like it. It says let P equal log base 10 of x, Q equal log base 10 of y, and R equal log base 10 of z. And they give us this expression that's currently in terms of x, y, and z, and they want us to write it in terms of P, Q, and R. What they're getting at here is they want to see if you can use your log properties. They want to see that you understand your log properties. So what they are asking you to do is see if you can split this whole equation right here, this expression, I'm sorry, and split it up so that it's in terms of this log base 10 of x, this log base 10 of y, and this base 10 of z. Well, right now it's all condensed as one logarithm. So in order to get it in terms of log base 10 of x, log base 10 of y, and log base 10 of z, you're going to have to split it up into multiple logs. So before we even worry about the P, Q, and R, we just need to worry about expanding that logarithm. So the first thing I'm seeing here is we have a quotient between the x and the bottom part, which is the y squared square root of z. So the first thing that we might do is we might go ahead and say, okay, I can split this using the quotient property into 2 logs, both base 10, because that's what our base is right here, like this. Now, once I split this into my 2 logs like I have here, I need to keep going as far as I can go. So the next step might be, okay, well, my log base 10 of x is fine. That's all done. But I need to split the next 2. And when I look at this y squared and z, square root of z, they're being multiplied. So I can use the product rule to split it into 2 logs that are being added. Now, I want you to notice here it's important that I kept these parentheses here because this subtraction applies to the whole log. So if I split that log into 2, that negative still applies to both of those logs. So I need to be careful with that. Now, I can go ahead and use power rule with the squared here, and I can bring that squared down into the front. Okay. And then right now, I can't do anything with that square root unless I rewrite it as a power. And we know that a square root can be written as a power of 1/2. I'm almost as simple as I can, but since we still have this power right here of 1/2, we should use the power rule and bring that down in front. So now we have log base 10 of x minus, and we still have those parentheses, 2 log base 10 of y plus 1/2 log base 10 of z. Once we do that, we can go ahead and we can say, all right, now that we've looked at that, we can replace log base 10 of x with p. We can replace this log base 10 of y with q. And we can replace this log base 10 of z with r. And so there is our expression entirely in terms of p, q, and r. So I can go ahead and say my final answer, I'll go ahead and write it up here, is p minus 2q plus 1/2 r. And for the sake of simplifying it fully, we should really just distribute that negative. So p minus 2q minus 1/2 r. And there's my answer. That is a very, very, very common IB style question. So you can definitely get more practice problems like that from your book, or see me and I can get you more. Okay, let's look at this second problem right here. Let me go ahead and rewrite that since I kind of wrote over it. It's hard to see now. Log base 2 of x plus log base 2 of x minus 2 equals 3. And notice this restriction right here, x has to be greater than 2, comes from the fact that if x isn't greater than 2, we get log base 2 of a negative. And part of our definition of a logarithm is that we don't have negatives there. So that's why that restriction is there. Now, when we look at this equation, we're trying to solve for x, but right now we need to simplify this because it's it's too complex. We can combine these two logs into one. So we want to condense. Now I'm noticing that we have this addition sign here, and that's telling us that we can use the product property to combine them. So product property says I can combine these into one log that is the product of the x and the x minus 2. And so I can simplify that. Log base 2 of, I can distribute that x to be x squared minus 2x. And so now that I've done that, I can go ahead and use our one-to-one property, which we've talked about, that to allow us to get rid of that log, because right now the log is getting in the way of us having x isolated. So we can raise everything on top of a 2 as a power of 2. So 2 to the log base 2 of x squared minus 2x equals 2 to the third power. 2 to the log base 2 just leaves us with x squared minus 2x. And 2 to the third is 8. So we're left with a quadratic that we can solve. We can take that 8 over to the other side, and we can factor. And we get x equals 4 and x equals negative 2. And then the only thing we have to check for is, do we have an extra solution that's not actually a solution? So let's go back up and look at our logarithms. Can we have a negative a log of a negative? No. So can x be a negative? No. So we can go back to our two answers and we can say, oh, we may have gotten x equals 4 and x equals negative 2, but we can't have x be negative because it'll give us the log of a negative. So we only have one answer, which is x equals 4. Those two problems are two examples of the most typical kind of log problems we've seen. Of course, there's lots more that we can do with logs. There's no way in a 10 to 15 minute podcast that we could cover everything, but that should give you a good idea or a good refresher on what we've learned. See me with questions.